We're going to continue with our look at Lewis dot structures. So far we've done atomic elements. We're now going to look at the diatomic elements and compounds that have covalent bonds. So starting off with our Lewis dot structure, let's quickly draw those for period 3. We have 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, 6 dots, 7 dots, and 8 dots. Now I've drawn the red line in, and that separates our metals from our nonmetals. And that's because it's going to tell us what kind of charges we can expect and how many covalent bonds we have, depending if it's a metal or a nonmetal. First, let's look at the expected charges. So all of these would like to get to 8 dots around them, or 0 dots. And the reason I say 0 dots is sometimes if you go back from, let's say, sodium, it has 1 dot. If I go back by 1, it ends up over here where it has 8 dots from the previous Lewis dot structure. So that's why we sometimes go up, sometimes down. So we look at the charges, we want to find out what's the easiest way to get to 8. In the case of sodium, if I remove 1 electron, it goes down to 8, but by losing 1 electron, that's a negative charge that is being lost, that means it becomes a positively charged group. So we get sodium expected to have a +1 charge so that it can lose that 1 electron. With magnesium, it's easier to lose 2 electrons than gain 6, so it's going to have a +2. And that is true for all of group 2. With group 1A is always going to have a +1, group 2A is always going to have a +2. Then we see the B group, and we'll talk later about those. Those are a little bit unusual. Then we're going to talk about group 3A, and again we expect it to have a +3 because it's easier to lose 3 than add 5. Finally, we get to the silicon section. Now this is group 4, and I can either lose 4 or gain 4. It ends up that these ones usually don't do either as long as they're small. But as you go down the periodic table, you get down to lead and those types of things, it will actually lose those electrons easier. And that's why it slides to the metal side. So you'll notice that that metal line, that stair-step line, goes to the right side as we go down the periodic table, and that's because those properties become more metallic because they can hold a positive charge more readily. So again, silicon can have either a +4 or a -4, and it will do both, or most likely neither. Then we can look at phosphorus. Now phosphorus, it's easier to add electrons because I can add 3 instead of losing 5. So when I add 3, it becomes phosphorus with a -3 charge. Then we go to sulfur. It has sulfur with a 2 negative because it only needs to add 2. You can see there's 2 spots where I can add electrons. And chlorine has only 1 spot left to add an electron, so it likes to have a -1. And the noble gases are noble, so they never get a charge because they already have 8 electrons. So those are the charges we expect if it makes an ionic compound. How do we know we have an ionic compound? Well, recall that we're going to start with a metal to make it ionic. So if we don't have a metal present, that means it must be a covalent bond. So how do we find those? The covalent bonds are going to be the things that start with nonmetals and have all nonmetals present. So let's look at those. So easily on this chart, we're going to get rid of sodium, magnesium, and aluminum. Those will not have covalent bonds because they are on the metal side. Then we're going to look at, let's say, silicon first. If we look at silicon, it has 4 dots that are single. They all need a partner. We want to get to 8, so they're going to have 4 covalent bonds for group 4A. Group 5A has 3 dots that are single. They don't want to stay single, they want a partner, and so we're going to see partnering up. So phosphorus likes to make 3 bonds. 2 of them are already lone pairs, so they're not going to pair up. We look at sulfur. It has 2 sets of lone pairs, but it also has 2 single electrons. Those 2 single electrons are looking for partners. They can't pair to each other because they come from the same element, and they have to be split according to a Lewis dot structure. So they're still going to need to find something to bond to, and so we see that we have the 2 pairs that are already paired together, and then these 2 will make 2 covalent bonds. And then finally with chlorine, we only have 1 single one, and so it wants to have 1 covalent bond. Let's look at the covalent bond. Covalent bond is a chemical bond in which 2 neutral atoms share electrons. These are sharing electrons, not giving and taking. They both are sharing. We're going to show a bond by drawing a line between the two atoms, and that will be a pair of electrons, one coming from each of the two atoms. Each of the bonding atoms will complete its valence shell, supplementing its usual number of electrons by sharing from the other atoms. That means we can add atoms to it without giving it a change in charge because it's sharing the electrons. It's giving away part of its electrons and it's accepting part of the electrons, but it gets to count both of those for every bond. For these patterns, what we're going to find is that every bonding atom will have 8 electrons around it, unless it's hydrogen, which only gets 2 electrons because it's in the first period. And if it's in the third or lower period, it can have more, but we will not be dealing with any of those in this course. So we're going to keep it simple and say everything gets 8 electrons around it except for hydrogen for this class. So I'm going to model this for some elements. We're going to make these 2 elements, A and X. Okay, let's bond those together. And now what I want to do is I'm going to put all the electron dots around it. In this example, they are both from group 7. So we have just one bond, and then we're going to count how many electrons there are. So on A, we have these 2, 2, and 2, that's 6, plus these 2 that count for it, that's its total of 8. And for X, we also have 2, 2, 2, and the 2 that are shared, and that accounts for 8. So we have our 8 valence electrons for each atom. Okay, let's start making some molecules. We're going to start with the diatomic elements. These are the atoms that come joined together as an element. Hydrogen's in a little bit of an unusual case. It's not going to have our 8. Remember, it only gets 2 as its maximum number of electrons. We're going to start by drawing the hydrogen. We're going to put 1 dot on for each of the hydrogens. Now what I like to do is I like to put those dots close to each other because they need to bond. And we're going to see that each of them have one single electron that needs to have a partner. And so we draw a line between them. We now count the number of electrons. This hydrogen has 2. This hydrogen has 2. It seems everything is satisfied, again, with hydrogen only getting 2 and not 8. And that is our whole structure. It's also good to always count how many valence electrons you have total. So each hydrogen has 1. On the end, we have a total of 2. And that is a correct structure. Now let's look at the halogens. They're the next easiest one. So for the halogens, that's fluorine, chlorine, bromine, iodine that we're going to be looking at. For those, we're going to know that they are in group 7A, so there are 7 dots. Let's go ahead and draw the 7 dots around the first one. I'm going to use chlorine as an example. So Cl, 1, 2, 3, 4, 5, 6, 7. And I'm going to leave that extra 1 off to the side. Do another one with chlorine, and this time we're going to leave that extra 1 towards the middle so that the 2 of them match up. So we have our 7, and now we're going to make a connection between those 2 single dots. And now when we count them, we see that the first one has 8, and the second one has 8. So each atom has its octet. Now let's just check that we have the correct number of electrons total. Each of the halogens had 7, so we need a total of 14. Here, let's count them. 2, 4, 6, 8, 10, 12, 14. And so we have the correct number of electrons total. Everything has its octet. This is a correct structure for chlorine. If I wanted to change it to fluorine, bromine, or iodine, all I have to do is change the letter in the middle, so the pattern is still the same. Okay, let's try oxygen. This one's going to be a little bit harder. It has a little bit additional step, so I'm going to watch for that. But the first step is to count how many valence electrons we have. Each oxygen has 6 for a total of 12. So we're going to be working with 12 electrons in here. We'll draw one oxygen with its 6 dots, so 1, 2, 3, 4, 5, 6. I'm going to leave the 2 single ones close to the other oxygen as I can. So it makes it a little easier if they're closer. It makes the drawing look nicer. Draw the other oxygen and put our 6 electrons around it. And again, we want to make sure that the one that is single is closest to the other oxygen. So we have 2 single ones. We're going to put them as close as we can. One here in the center, and the second single one could either go on the top or the bottom. Well, it really depends on where you put the first one on the other oxygen. So we have our other oxygen, we have two of them that are ready to bond. We want to make sure that when I have the single one, if let's say it's on the top, then this one should also be on the top. But if that single one's on the bottom, then my other one should also be on the bottom so that they can connect and make a bond. Remember, all of the single electrons need to find a partner from another atom. So we're going to have them bond up, and that's why we want to make them easy to attach to each other. If I have one on the top and the bottom, then the line has to go through the middle and it looks really sloppy, so we don't do that. So let's go ahead and draw that out. So right now we have our 6 electrons here, our 6 electrons here. We need to get to 8, so we're going to put a bond between these two. That's the obvious one. And that only gets me to 7 bonds each, so I need to make one more, and now I have another one. We call this a double bond when there's 2 bonds between 2 atoms. So we have a double bonded oxygen, and that is our structure. Let's make sure that everything has its octet. So here we have 2, 4, 6, 8 for this oxygen, 2, 4, 6, 8 for this oxygen, and they each believe that they have their octet, so that's good. We can check that off. And then the last step is to make sure that we have the correct total number of electrons, and we should have 12 because each oxygen provided 6, so we have 2, 4, 6, 8, 10, 12, and it is correct. That should be our correct structure. In this case, oxygen is the only diatomic found in group 6A, so that's the only one this will model. So I'm going to have you try nitrogen. Go ahead and pause the video. Okay, let's start with how many valence electrons does each nitrogen have? Well, they each have 5, so we'll put our 5 down. That means we have a total of 10 valence electrons to work with. We're going to write our 2 N's down. I'm going to go ahead and bond those 2 nitrogens together. I know that they have to be at least one bond between them. I'm just doing that to make it easy to structurally find it. So we'll go ahead and put those in, and we're going to put 5 electrons around the first one. So 1, 2, 3, 4, 5. Now the 5th one, where should it go? The best plan is to put it away from the other nitrogen. So we know where the other nitrogen is. We want to put it away from that so that the singles are as close as they can be to the nitrogen they're going to bond with. But our other nitrogen, again, we're going to have a single on the top, a single on the bottom, the single in the middle that we already have, and then the 2 that are going to be on the outside should be your paired ones. And that's it for that structure so far. So now we want to make sure that they have their octet. If I bond these 2 together, we now have 7 for each nitrogen. I bond these 2 on the bottom, and now every one of them has 8. Let's go ahead and count them. So we have 2, 4, 6, 8. That's an octet. And 2, 4, 6, 8. And that's an octet. Each atom has its octet. Now let's just go back and make sure that we have the correct total number of electrons. Let's count them. 2, 4, 6, 8, and 10. And that is our correct number. This should be a correct structure. It is a triple bond between those 2 nitrogens. You can never have more than 3 bonds between 2 atoms because those 4th ones can't reach around to connect. So we should never have more than a triple bond. The only diatomic element in group 5A is nitrogen, so it will not be modeling any other elements. And that is the last of our diatomic elements. Now we're going to move into some other molecules that are joining different atoms together. We're going to see how we do those. We're going to look at something called the binary compounds. What I mean by binary compounds are compounds that have 2 different elements bonded together. There may be more than 2 atoms total, but they are from 2 different elements. For these binary compounds, the first step is a new step. What we need to do is find out what atom goes in the middle and what gets bonded to it. The rule we have for this is to place the first element listed in the center, that'll be your central atom, unless the first element listed is hydrogen. So this is an example of the exception first. We're going to start with the oxygen in the middle for this one, and we're going to attach the 2 hydrogens to it. So we have the oxygen, we have the 2 hydrogens. I personally like to actually make the bond between them because I know there has to be at least one bond. For it to be a compound, it must have a bond between those 2 atoms. So we're going to go ahead and draw those in as bonds for the moment. That's going to count as our 2 electrons. We want to now find out how many total electrons do we have to work with. So each hydrogen has 1, so for a total of 2 from hydrogen. Each oxygen has 6 valence electrons for a total of 6, because there's only 1 oxygen. We add those all up and we get 8 electrons that we're working with. I'm going to start by drawing out my Lewis dot structure for oxygen. So we've got 1, 2, 3, 4, 5, 6. So 2 of them are already in bonds because I bonded them to hydrogen earlier. And then we're going to look at hydrogen. Each one of those has 1 electron that is being used for the covalent bond. So we've got all of our bonds already used. Now we're going to look at their octets. Remember, hydrogen gets a duet, just 2 electrons instead of 8. So we have 2 here, 2 for this hydrogen. And when we look at the oxygen, it has its 8. So everything is satisfied as far as the octet goes. Now all we have to do is check that we have the correct total number of electrons. So let's go ahead and count that. 2, 4, 6, and 8. And we are correct. This is a good structure for water. This may not show the exact structure of water, but it does say how the hydrogens are attached to the oxygen. Notice that we could have drawn the hydrogens either far apart, as my structure here, or we could have drawn them bent or close to each other. Both of these are technically correct for a Lewis dot structure. The more accurate structure that we'll discover later is this bent shape, so that's a more accurate structure. When you're providing the answer on the test, I don't want to see the circles around these electrons. That's not what I'm looking for. Those are just to show you how to count the number of electrons. So what I expect to see is something like this. I'm skipping letter B for a moment because it's a little more challenging. We'll do it last. So let's try the next one. Letter C. We have CH4. The one that goes in the middle is the first one listed, as long as it's not hydrogen. So we'll put the carbon in the middle. I'm going to go ahead and attach all 4 hydrogens to it to the 4 sides. And then we're going to find out how many total electrons we should have. So carbon has 4. There's times 1, so we got a total of 4 coming from carbon. Then we're going to look at hydrogen. Each hydrogen has 1 valence electron. There are 4 hydrogens. Our total then is 4 valence electrons from hydrogen, plus our 4 from carbon, and that gives us a total of 8 valence electrons to work with. So right now, we look at our carbon. We would put our 4 dots around it, so 1, 2, 3, 4. Those are already all bonded, but we know that they're going to be there. And now we put 1 electron on each hydrogen, 1, 1, 1, and 1. They're all where they're going to be bonded because they have to be bonded to that carbon to make it a compound. So we know that it's bonding. So there we have those. And now we just go back and check that we have octets, or in the case of hydrogen, a duet. So here we see 2 for this hydrogen, 2 for this one, 2 for this one, and 2 for this one. And then we look at the carbon, and it has 1, 2, 3, 4, 5, 6, 7, 8, or 2, 4, 6, 8, depending on how you like to count it. So we've got those 8 electrons around carbon, which makes it its octet, and everything is satisfied. The last thing is to check that we have the correct number of total electrons. So here we see 2, 4, 6, and 8. We are correct. And that is the structure for CH4. I'm going to have you try NH3, so please pause the video. All right, so step 1, find out what atom goes in the middle. And we're going to put nitrogen because it's the first one listed. Then step 2 is to attach all of the other atoms to that center atom. So go ahead and put those on. We've got our 3 hydrogens. We're going to bond those together. And now we want to find out how many total number of electrons we have. Each nitrogen has 5 times 1, so we've got a total of 5 electrons, plus hydrogen. Each hydrogen has 1 valence electron, times the fact that there are 3 of them, so there's 3. 5 plus 3, we get a total of 8 valence electrons that we're working with. So let's do our Lewis dot structure for nitrogen. We're going to ignore the hydrogens for the moment. We're going to count how many electrons we have. So nitrogen should have 5. We're going to go 1, 2, 3. Those are the previously bonded one. 4 and 5 will be sitting here. And those are going to be our extra electrons, lone pair electrons that do not bond to other things. And then we go to the hydrogen. We put 1 dot for each of them. 1, 1, 1. So they all have their electrons to start with. We can see that they are already bonded, but that helps us to know what's going to bond and where. And so here we're going to count. Now let's check for octets. We have 2 for hydrogen, 2 for hydrogen, 2 for hydrogen. Those are all correct. And for our nitrogen, we have 2, 4, 6, 8. That is correct. And so we have everything has its octet, or in the case of hydrogen, duet. So we've got that checked. Next step, we need to see if we have the correct number of total electrons. So let's go ahead and count them. Each bond counts as one pair of electrons. So we go 2, 4, 6, and 8. We have 8 valence electrons, which is what we had to start with. So this is a correct structure. And again, this is how it should look when you turn it in on the test, not all of those circles. In this structure, how many lone pairs of electrons do you see? That's right, you should only see one set of lone pair electrons. How many bonding electrons do you see? Correct. There are 6 bonding electrons to form 3 bonds. Okay, you should try letter E, CCl4, and see how you do. Okay, let's start by picking our central atom. That should be carbon, because it's listed first and not hydrogen. So we put carbon in the middle. We're going to go ahead and attach our 4 chlorines to it. I'm going to go ahead and bond them so you can see them. 1, 2, 3, 4. And then we're going to put in our electron dots. So let's count how many we should have for carbon. Carbon is in group 4A, so it should have 4 valence electrons. There's only 1, so it counts as 4. Each chlorine should have 7 valence electrons. So 7 times 4 is 28. We add 4 plus 28 and we get 32 valence electrons that we're going to be working with. So let's start doing that. We put them around carbon. We have 1, 2, 3, 4. Those are already bonded, so we don't have to do anything more with that. Then we look at each chlorine and we see that there's 1 already there. I'm going to put the other 6 around as pairs. So 1, 2, 3, 4, 5, 6. And we see that we have our structure for chlorine. Now that will be the same on all of the chlorines because they're all the same atoms. We're going to go ahead and do that. 1, 2, 3, 4, 5, 6, 7 for that chlorine. 1, 2, 3, 4, 5, 6, 7 for that chlorine. 1, 2, 3, 4, 5, 6, 7 for that chlorine. And 1, 2, 3, 4, 5, 6, 7 for that chlorine. So they all have all of their electrons now, as our normal Lewis dot structure would show them. We see that there is a bond between the carbon and the chlorine, so we're going to count those. So now let's check that everything has its octet. We'll start with this chlorine over here, and we see there's 2, 4, 6, 8 electrons here. That's going to be the same for all of the chlorines, but I'm going to go ahead and draw them out. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Each chlorine has its 8 valence electrons. Let's just check that central atom. And we see there's 2, 4, 6, 8 valence electrons there, so that everything has its octet. The last step then is to check that we have the correct total number of electrons. So we should see a total of 32. If I count around this chlorine, that one's 8. The next one has its 8, the next one has its 8, and the next one has its 8. 4 times 8 is 32, so we know that we have the correct number of electrons total, and that is our structure for CCl4. Now we get to go back to the one that's a little bit harder. So we're going to start with the same rule. We're going to put carbon in the middle because it was listed first. We're going to attach our 2 oxygens to it. So we see it like this. Now we're going to count our total number of electrons that are available to work with. We see 4 valence electrons for carbon. There's only 1 carbon, so a total of 4 valence electrons coming from carbon. From oxygen, we see it's a group 6A, so there's 6 valence electrons times the fact that there are 2 of them, for there's 12 valence electrons that come from oxygen. We add that together. 4 plus 12 is 16. We have 16 valence electrons to work with. Let's go ahead and do our carbon first. It has 4 valence electrons, so we're going to put 4 dots around it. 1, 2, 3, 4. We already have these 2 that are bonded. Don't worry about it. We just know that there are 4 around that carbon first. Now let's do our oxygen. In the case of oxygen, we're going to put our 6 valence electrons in. Here's our first one, already in the bonded form. Then 2, 3, 4, 5, and 6. And then we have all of our electrons around that one. And now let's do the other oxygen. We've got 1, 2, 3, 4, 5, 6. We've got all of our electrons. Now we do have a question of where to place the doubles and the singles. So on the left-hand side, we see that the single electron is at the top. On the right-hand side, if I put it at the top, when it tries to bond, it's going to try to bond to the same electron as the other one does. So I'm going to put this one on the bottom. That way it can bond to the electron on the carbon that is free and not already bonded. So that's how I choose it. Again, you can do it differently, but you'll probably end up going back and erasing so that you don't have these big X's in your bonds. Okay, so let's count the number of electrons that we have on oxygen. Right now, this oxygen believes that it has 7. It needs to have 8. You can see this one is single. It needs to find a partner. It partners with that one extra one on the carbon there. They're going to bond, and now that oxygen thinks it has 8. This carbon still thinks it has 7, and this oxygen still thinks it has 7. So we need to make another bond between those. You can see they each have a single electron ready to bond. We make a bond between those, and we find that now this oxygen has 8. Let's just check that carbon in the middle. Does it think it has 8? And it does. So now we've got our octet for each atom. So let's go ahead and count that we have the correct number of electrons. We have 2, 4, 6, 8, 10, 12, 14, 16, and that is the correct number. And the last thing is just to notice that we do have 2 double bonds here. Now there are several ways you can show this to me. You can draw it like this, like we originally had before we had the circles, or you can draw it just simply like this. And that is it for Lewis dot structures for covalent compounds.